Hello, everyone. My name is Jason Iaconis. I'm an application scientist at IMQ, and I created this first challenge problem on quantum state tomography, and I'm going to go over the solutions now. So this problem is all about taking an unknown quantum state from a couple of different classes of possible quantum states and figuring out how, by measuring these states in different ways, without actually knowing what the wave function is, we could find a quantum circuit which reconstructs the wave function. So very generally, our state here is this U hidden operating on the all zero state. We want to find, without knowing what U hidden is, a circuit U gen for generating an unknown state, where when we apply it, the dagger to this state, basically disentangles this wave function, or once again creates the all zero state. And so this problem was built up in a few different ways. But the first kind of warm-up problem was to take a quantum state with just a single qubit, which you could write as A plus B Eli theta, and figure out just by measuring this state in different bases what this wave function is. So I'll go over the solution here in this code. So this code here first, it's written all in Qiskit, and here I'm just importing a bunch of different packages, mostly just Qiskit libraries that allow us to solve this problem. So in problem one, yeah, we have this wave function A0 plus B1, right? That's how we want to write it. And the important thing to note is that A could basically be treated as a real positive number because there's a global phase that doesn't matter for these wave functions. But B is a complex number, so we could write it as a magnitude plus a phase. So the way we're going to measure this, when we measure in the Z basis, so just take shots on this wave function, we get the magnitudes A and B. It's just the square root of the number of shots on the bit string 0 and 1, respectively. But we also need to figure out what this phase theta is. And to do that, we're going to apply these two operators, the Hadamard operator, and measure that circuit, this circuit with Hadamard at the end, and also the SH operator, and measure that at the end. And when we do this, we get A plus, like the Hadamard circuit is going to transform this wave function to interfere these two. So we'll get the amplitude for the zero state will be A plus B, and the one will be A minus B. And then when we apply the SH operator, it's going to be A plus IB and A minus IB on the one. And the important thing here is when you measure these two things, for the Hadamard operator, that's going to give you basically the real part of the B, the relative phase between the two, plus these, which is just one. And then the SH is going to give you the imaginary component. And putting these two together, we measure cos theta, sine theta here. We'll be able to figure out what theta is. And from that gives us the full wave function. And we could, then create a circuit from this wave function that would disentangle it. So here I'll show you, basically go quickly through the code that performs this. So this is what I gave you. It's just creating a random 1D circuit to create a random 1D wave function. Now I'm going to create my list of operators here. So I'm just going to measure in the identity basis, the Z basis, to get the amplitudes. And then at the end, I'm also going to apply either this Hadamard or this SH operator. These are going to be appended to the end of the hidden circuit, and then we're going to measure in the computational basis. Right, so we're going to set the shots for each one of these to just be 100 and get histograms from all three of these measurements here. And then once we do that, we're going to take the absolute value of these amplitudes from the first measurement, and then the real and imaginary phases from these other two measurements, basically. So these are just the histograms from these three operators. And then from these, all these operators, I'm going to just invert these equations up above. I added a little small number here in case you get 0 shots from on one of these basis states. This will basically fix that problem for you. And then we get the cosine and the sine up above. We want to do a little bit of fixing to make sure you're in the right domain here. That's all this does. Make sure you're in the right domain, and then adjust it based on relative signs here, basically. So you apply this whole thing, you need to take a little bit of care to make sure, you know, your arc cos and arc sine act the way you want them to do. But when you do that, you know, we now basically, without knowing what the wave function was, you got all this information, A, B, and theta, from these functions here. You can pause and look at exactly how these functions are implemented if you want. And then we're gonna, you know, just take this prepare state function on your reconstructed vector, right? So a reconstructed vector is the absolute values times this phase, which is 1 and e to the I relative phase here. We apply this and then use this give score function, which will apply this and see how close this expectation value is to 1. The closer to 1, the better we reconstructed. And we'll see here, we basically got it basically perfectly with 100 shots, 0.998. That's basically perfect reconstruction. So that was the first challenge problem, kind of the warm-up. We upped the complexity in part 2 by a little bit. Here we now have a 2-qubit state, and we want to do basically the same thing, figure out what these amplitudes are. Again, we could treat A as being positive and real because it is that up to a global phase. But B, C, and D now are all complex numbers. So we need both the magnitude and the phase. I think in the challenge, I started off saying, imagine that they're real, but they could be negative. But then in the third part, we want to know what happens when they're completely complex. I'll just do the complex case here. It's basically the same. And the procedure is pretty similar. You know, we measure the computational basis, and that gives us the amplitudes A, B, C, and D. And then to get the sign and phase information, we're just going to apply these 4 operators here, which is Hadamard's on the 2 qubits and this SH operator on the 2 qubits separately. Nothing applies both at the same time. And so, for example, when we apply just a Hadamard on the first qubit, what that does is, again, interferes these amplitudes in a way. You're basically interfering the A and C amplitudes and the B and D amplitudes. Right? So that's going to give you the relative phase between A and C and between B and D. And similarly, when you apply the second Hadamard operator acting on the second qubit, now we interfere A and B and C and D. And that plus do the same thing with the SH operators is going to give you the imaginary component, is all the information you need to reconstruct these states. Because you know the amplitudes, and now you know the relative phases between A and C. That gives you just the absolute value of C. A and B, that gives you, you know, everything you need to know to calculate B. And then to get between B and C, you could just note that you know the relative phase between B and C and B and D also here, right? Like, B and D you get here, and you know B, so that gives you C, and then well, that gives you D, and then relative CD here, and you know D now, so that will give you exactly what C is. Basically using the same procedure as above, right? So these measurements are basically enough. So we'll go through this code again. Here's a 2-qubit random circuit that was provided for you, which will just create a random 2-qubit state. And now we're just going to get the histograms from these 5 measurement bases that I showed above. The identity basis, H0, SH0, H on qubit 1, SH on qubit 1. And then when we apply this at the end of the circuit, it's going to give us these expectation values. Okay, so here we actually just measure all those histograms that I just listed above. And then we're going to do the same processing of this histogram, right? We want the real part of the phase and the imaginary part of the phase for these 2 scenarios here above, where we apply the Hadamards on, or the operators on the first qubit and the second qubit respectively. And that's going to give us all these relative phases here. And then, right, so this is just giving us these numbers from the histograms. And then when we go back, we get the cosines and the sines of these relative phases for A, B, you know, for these 2 operators up above. And again, we're this cos phase difference, sine phase difference are the differences between all these phases here. So you go through all this math, but you're basically just inverting the same equation that you did before here, but now in a more complicated form because you have more relative phases that you need to figure out. But once you get these, you can do the same thing, just reconstruct exactly what these probabilities are. P01 is the theta value up above for the 0-1 state, so the B. Similar for 1-0, which is C, and 1-1, which is D. We'll reconstruct those phases. We know that magnitudes of A, B, C, D from our computational basis measurement. We put those together, and that gives us our reconstructed vector. So we'll see that working here with 2 qubits. This is basically our vector. This is the quantum circuit that we get from that prepares that vector. And then we see when we apply it to the hidden score, here we got 98%. Usually you get above 99, but this probably was a little bit unlucky with just 100 shots. That's pretty good. And so that pretty much solves problem 1. There was one third component, which was figuring out how you could extend this if you have more qubits. And basically the answer is, you'll need an exponential number of shots in general when you have large numbers of qubits because these magnitudes will be much smaller. But the number of different bases you measure in is actually just scaling, at worst linearly with the number of qubits, because you could just apply these single Hadamard and single phase qubits, and each one is going to give you a bunch of relative phases between two different pairs of amplitudes, right? And then you just need to look for these collisions, right? Like this gives you C, and then this gives you BD. This gives you B, so then you know D, and then you know the collision between C and D. It just keeps extending like that, right? You get all these collisions, and you just need to make a chain where you could figure out the absolute value of everything, linking it back to the A, which you assume is a real positive number. So with just a linear number of measurement bases, you could measure arbitrary states. So that's the solution we're looking for, is that you basically don't need an exponential number of bases measurements in number of qubits, just a linear number. Okay, so let's go on to problem 2. So problem 2 here was looking at graph states. Can you do tomography when you just have a graph state? And a graph state is a wave function that has this form. You basically just apply Hadamard states and these CZ operators. These are all what are known as Clifford gates, right? It's a class of gates that could actually be simulated classically. And because it has this structure, we could actually do the tomography efficiently, even when the number of qubits of the state is very large. So I'll go over exactly how you do this here. So here I'm just going to generate a Clifford state. I'll show you exactly what one of these circuits looks like. Here we apply, 10 qubits, and we're applying 7 different operators. You can make this as long as you want. But yeah, this is basically the hidden state that we're going to try and reconstruct just from measurements. And the key here is that these graph states are defined as eigenvectors of what are known as stabilizer operators. And in particular, a stabilizer operator is just a string of Pauli operators. But for graph states, these stabilizer operators have this specific form, which is an X operator, an X Pauli operator on one of the qubits, and then a product of Z operators on all edges connecting to that ith qubit for some graph G. So basically, there's a hidden graph that defines what this graph state is. And once you know that graph, you know that that state is the +1 eigenvector of all these stabilizer operators. And so if you figure out what the stabilizer operators are, you figure out what the graph is. And once you know the graph, you could create this state, this graph state, by just acting this equation on it. And so we need to figure out from different measurements which of these operators are the stabilizers for this hidden graph state. And we could do that by just probing in n different bases, where for each different measurement, we're just going to apply an X operator on a single node and then measure in the computational basis. And when we do that, this stabilizer operator becomes something like this, an operator like this. And from these measurements alone, we could measure all these expectation values for every possible graph on these J qubits. Now, measuring every possible graph is an exponentially hard thing to do classically. But because, we're up to 20 qubits or so, we could just measure every possible graph on those qubits and measure all these operators. And we're allowed to do exponential classical processing as long as the number of bases and the number of measurements on the quantum circuit is not exponential. And of course, there's also ways to not get around this exponential classical processing. But the simplest way is just to measure every possible graph and measure these operators. So I'll show you how this is done here. So here, we just apply Hadamard's on one of the qubits to rotate this X into this Z operator. And then we're going to, measure the histograms for all these operators. And then here, this is going over the possible graphs here, like the possible stabilizers, and basically just, taking those shots and measuring this operator. So if there's a 1 on the I when there's a Z operator, you apply a -1 factor to that histogram, that bit string. And if there's no Z operator, you just count it as a +1. Or if it's a 0, you add a +1, right? So we're calculating all these expectation values, but you could do it just from these histograms that we already have. And then you're going to do this for all the circuits here. This is just going through and applying this check edges. I'll show you in a second, actually, how this is done. But here, I'll just show you, once you have this, we figured out, this tells us, if our stabilizer operator should be +1, right? So if that stabilizer measurement is greater than here 0.95 and less than 1.05 times our 100 shots, like that's the expectation value, then we know that that edge is going to be in our graph. And so we're going to include that in our graph and apply this CZ operator on that edge. And you see here, this is the circuit that we found from our graph state, just from our measurements. And to compare, this was the original graph state. Now, they don't look exactly the same. That's because some of these edges actually cancel out. But you'll see, and the order could be switched because these operators all commute with each other. But we'll see that the score it gives is 100%. And let me just show you on an even simpler example. Let's go depth 4, or 4 qubits and 3 edges here. It's just here. Yeah, I'm going to print this edge. Yeah, and so this is what I want to show here, which is if you look at this histogram, for example, for the first operator where we apply, there's always going to be an operator on the 0th qubit here. So this will always be 1 in our measurements. And basically, if this subgraph, like here, there's an edge between qubit 0 and qubit 1 in this graph, right? And for example, and because of that, that edge is in here, you get 100 shots on this like each one of these bit strings represents a subgraph, right? And if that subgraph is in here, that means that stabilizer is what you're measuring, and you get all 100 shots, add up coherently. And so this tells you what the edges are in your state. Okay, on to problem 3. So problem 3 is actually the hardest of it, of the 3. This is here, we have a low depth brickwork circuit, right? So I showed you exactly what it is here. You just have 2 layers of these nearest neighbor gates applied between pairs of qubits. So for example, on 10 qubits, our circuit's going to look something like this. And we want to figure out exactly what this circuit is. So how could we do this? It's actually, it could be pretty tricky, but I will, and there's many different ways you could do it. In fact, some people gave solutions where you just apply a variational circuit and try to disentangle this and minimize some gradient function. And that's a valid approach. The problem is it's not going to work all the time, and it's going to be harder as you add more and more qubits to actually find this gradient going to zero. But it's definitely a good attempt at this. There's actually a deterministic way you could do this. And the key is to realize that because it's a low depth circuit, each qubit is only very lightly entangled with all the other qubits. And what that means, basically, is that you could apply like local operators that do pretty well at disentangling that qubit from the other ones. And the way you figure out what that operator is you're going to measure the 1 and 2 qubit reduced density matrices for all the pairs of qubits. And when you do that, you could then figure out what rotation you need to apply to disentangle this state. So like one kind of simple way that's not going to work perfectly, but will kind of work, is for every qubit, you're just going to measure the single particle density matrix, which means you measure the Z operator, the X operator, and the Y operator on each qubit. That gives you a matrix, this density matrix here, which tells you in which direction the qubit points on the Bloch sphere. But because your state's entangled, it's not going to, the moment is going to be reduced, like but it's still going to point in some direction. And if you take this, diagonalize it, and then apply the inverse of that diagonalized operator to your circuit, or to as a single qubit rotation, you'll basically rotate your spin, your qubit, to point in the zero direction along the Bloch sphere. When you do that for every qubit, you're basically going to partially disentangle your state, or you'll maximize the score as well as you can do just using single qubit rotations. And all it does, all you need to measure is the Z, the X, and the Y operators. So I'll show you how well that works. It actually works quite well, but it does depend. So this score here is just, if you just take a random circuit that has, or if you just take a like no circuit, basically, you'll get a very low score. If you just try and take an empty circuit, right? What is the overlap of this with the zero state? It's only 3% here. But now if we measure this X, Y, and Z operators and create this density matrix, that's what I'm doing here, is I'm creating the density matrix for each qubit. And then here you see I take that density matrix for each one, I find the eigenvectors, and then I apply the unitary based on those eigenvectors to disentangle, to rotate that qubit back in the Z direction. When I do that, I got 52%, which is pretty good, actually. You could do better, though. But the better solution is pretty complicated, just as a warning. But you could figure it out. Basically, what you need to do is measure the 2-qubit density matrix and then do the same procedure. So for every pair of qubits, you're going to measure all these operators on those 2 pairs of qubits, right? So here there's actually 15 different operators plus the II operator, which is always 1. You're going to measure that on every pair of qubits. Take that 2-qubit matrix, here it's a 4x4 matrix, right? Diagonalize it, and again, rotate back so that those 2 qubits point along the 0, 0 direction. And because you only have 2 layers of your Brickwork circuit, what that means, and it's a little bit technical here, but what that means is that this density matrix is a rank 2 matrix. And what that means is that there's only 2 non-zero eigenvectors of this matrix. And so when you apply this U on the edge qubits and rotate back, you'll completely disentangle that state. So you'll perfectly make that state point along the 0 direction. And then you do that for all pairs of qubits, right? Now, this is 15 different bases you have to measure in, but a lot of these commute with each other. Like you can measure XX, YY, and ZZ with just one operator by measuring in the Bell basis. Similar for zx, xz, yy, zy, yz, xx, and xy, yx, zz. So this is a lot to take in, but basically, you measure all these operators, you find this density matrix, you diagonalize it, and then you disentangle by applying that operator on the edges of the qubits, and go through and do that for every pair of qubits. And by doing this, you could completely disentangle your state just from these measurements. So I'll show you how it works here. Here I'm calculating the density matrices from these measurements. Here you can see I'm measuring these operators, right? Like pairs of operators, xx, xy, xc, yx, right? All pairs of these four. So here I got my list of density matrices. I disentangled it with these unitaries. And I found this circuit, QC dis, which is going to disentangle my state. And you'll see when I apply it, I get 84%, which is much better. It should be 100%, but because I'm only taking 200 shots here, 100 times 2, because I actually had extra basis measurements I could use. There's some noise in this disentangling circuit. I'll show you if I increase the number of shots, for example, up to 1,000. I think I could do this here. Let me see where. Here. Let's increase this to 2,000, and we'll actually get, we'll generate a new circuit, but we'll see. That will actually do much better. Let's see here, that only gave 20% using the 1-qubit density matrix. But here we see we got 92%. So this method works. But of course, there's other methods you could do that will allow you to partially disentangle. This 1-qubit density matrix example I gave above is one. Applying a variational circuit is another. And you can come up with other creative solutions, because at the end of the day, the fact that this circuit is lightly entangled is what allows you to do this tomography. So that is everything I wanted to show. That was the solutions to problem one or challenge one. So thank you, everyone.